thermodynamics. That was wild applause for those of you at home. Okay, so I know it's been a while, but thermodynamics, our last sort of major conceptual topic for the year, and then the rest of the year we spend on just specific reaction types, so acids and bases, solubility, and some electrochemistry. So this is our last real big one. The AP curriculum is divided into these 6 big ideas. So this, for them, is big idea number 5. Big idea number 6 was equilibrium. We just talked about that. We're going to talk about thermodynamics now, and we'll actually tie those two together. Big idea number 4 was kinetics, just to give you an idea. So the way they stated is the laws of thermodynamics describe the essential role of energy and explain and predict the direction of changes in matter. Thermodynamics is hopefully going to explain for us how you predict if a reaction will happen or not, and explain why such and such a reaction happens and why such and such a reaction doesn't. That's our goal. If we do this right, it'll change the way you look at why everything happens. So this is going to be a lens for us to look at reactions and think about why they happen. That's the broad idea. Now it says the laws of thermodynamics. Now if you type into Google the laws of thermodynamics, you'll probably come up with these 4. Don't ask me why someone put the 0th and then the 1st and 2nd, 3rd. I think the 1st and 2nd were like the established ones, and then the 3rd, they're like, oh yeah, wait, this other thing we need to throw in as a law. And then someone else was like, wait a minute, I think there's one more that we need to add, but we'll put it even before. I don't know. We're not really going to talk about the 0th law of thermodynamics. I just put it on here in case you like poked around and you're like, wait, isn't there a law we haven't talked about? 0th law of thermodynamics basically says if A and C are at thermal equilibrium and B and C are at thermal equilibrium, then A and B are also at thermal equilibrium. It's like the transitive property of thermal equilibrium for math speak. It's kind of obvious, and we won't really talk about it any further than that. We will spend most of our time talking 1st and 2nd laws. So 1st law of thermodynamics, energy of the universe is constant. 2nd, the entropy of the universe is always increasing. Now with both of these, there's actually lots of different ways you can state them, and there's more formal ways to state them. I've chosen these particular ways, and we'll explain each one. We haven't really defined entropy yet, so we'll come back and explain that one. And then the 3rd one, entropy of a perfect crystal at 0 Kelvin is 0. That's kind of a technical definition that I'll explain why it's somewhat important to us, but it's not one that's going to take up a lot of our time and energy. 1st and 2nd are the ones that are going to be most important to us. So we'll kind of focus on each one individually. Just to give you an idea of the cast of characters, I'm going to skip that slide. I'll come back to it. To give you an idea of the cast of characters, since they're kind of mentioned in the laws of thermodynamics, enthalpy is the one we've talked about already. And today we're going to focus mostly on the enthalpy. We'll get a little bit into the entropy side of things. But enthalpy we think of as a measure of chemical potential energy. If you look up enthalpy, look up a definition of enthalpy, that's not what you're going to find. But for our purposes, that's pretty much the way it's going to show up. Entropy is essentially measuring the disorder or the randomness of a collection of stuff. And it turns out randomness is kind of important because the universe tends to get more and more random as time goes on. And then Gibbs free energy is going to be this construct that we put together to tell us which way a reaction wants to go. So we'll think of it as a driving force for a reaction. So those are the characters, and we'll come back to each one. I just wanted to put them out there up front, let you know some of the terminology. But if we focus on the 1st law for a second, energy of the universe is constant. What's another way to state that 1st law? Energy cannot be created or destroyed. So the consequence of that is if a system gets energy from somewhere, that energy had to come from somewhere. It couldn't have just appeared out of nowhere. And just so we're clear, because we haven't reminded ourselves of this definition in a while, what does energy actually mean? Alex? The ability to do work. And what does work mean? All right, to exert force on an object over a distance. All right. And what happens to an object when you exert a force on it over a distance? It moves. So we will think of energy, even though it's not a technically rigorous definition, as the ability to make stuff move, right? We said that at the beginning of the year. Energy is the ability to make stuff move or to make stuff accelerate. You exert a force over a distance, you make it move. So if you want to make something move, what the first law is saying is you've got to find a source of energy. You can't just make it move without getting that energy from somewhere. So I wanted to get to school today. I had to get in my car and make my car move here. Where did the energy for my car to move here come from? Gasoline. Actually, it was stored in the gasoline and the oxygen in the air. Those two things together have this potential energy that was released, and I use that to get here. If I don't have that source of energy, I can't get here. A lot of times, this will be paraphrased as you can't win. Or you can't get something for nothing. Whatever energy you need to use, you got to get from somewhere. So that's the first law of thermodynamics. And we talked about that from the very first day of school, so I think we're probably in pretty good shape with that one. All right. First law mostly is going to be related to enthalpy from our standpoint. So we got to remind ourselves what enthalpy is. We did a quick unit on enthalpy. I think it was chapter 11 on enthalpy before. So the first half of this lecture is going to be just reminding ourselves of what we already know about enthalpy, maybe adding a tiny bit to it. So enthalpy is this term for the total energy in a system. And for us, really, we're going to think of it as potential energy. Okay? Again, it's not a rigorous definition, but that's the way it's going to manifest itself. And that potential energy really comes from the attractions and repulsions between atoms and molecules. Mostly attractions, but sometimes repulsions. That's where that potential energy is stored. It's stored in the way atoms and molecules are arranged and bonded to each other. Enthalpy symbolized by H. We'll talk a lot about delta H. We talk lots about changes in enthalpy in this unit. One thing you want to know is that enthalpy change for a reaction is independent of how the reaction gets from point A to point B. We relate potential energy a lot to gravitational potential because it's something we have experience with. So if you were on the first floor this morning and you needed to come up here to the fourth floor, you needed to change your potential energy by a certain amount. Doesn't matter which stairway you came up. Doesn't matter if you went up one stairway to the second floor and then down the hall and up another stairway to the fourth floor, your change in potential energy between the first floor and the fourth floor is the same, regardless of which path you took. And that's also true of enthalpy changes for reactions. So a lot of times we will use that fact because we can put two reactions together that still get us from a certain set of reactants to a certain set of products. Doesn't matter if we put together two reactions to equal that other reaction. The overall delta H will still be the same. And then we've talked already this year about two different ways that we can find delta H for a reaction. I'm going to add a third one today. So the two that we've already done, calorimetry and then bond energies. And then I'll talk about something called enthalpy of formation today. Okay. So calorimetry. Let's see what we recall. Let's break down the word. Calor. What does that mean? Heat. And then metry. I hear whispers. Measurement, yeah. So calorimetry basically means heat measurement. So how do I measure heat? Do I break out my heat-o-meter and just say, heatometer, tell me how much heat is involved in this reaction? It would be nice, but I can't do that. What do I need to do? What can I measure that I can then relate to heat? Temperature. Specifically, I can measure changes in temperature. So what was that relationship between heat and change in temperature? Q equals mc delta T. So with calorimetry, we're using this equation, Q equals mc delta T. All right. So in this equation, we had Q, which stands for quantity of heat. Sorry? It's not. It's usually a lowercase q. Could be a capital Q in some cases, but usually a lowercase q. M in this equation stood for what? This is the mass of the substance changing temperature. All right, C, specific heat capacity of that substance. And then delta T is change in temp. Sometimes we use a device called a calorimeter that has a bunch of substances in it, and so we can't use mc delta T, but we can measure the entire heat capacity of that calorimeter. And so sometimes we'll just use the alternative equation that's Q equals big C times delta T. In that case, big C would be the heat capacity of an entire calorimeter. Yeah, so we did a procedure that kind of gave you an algorithm for finding the C of the calorimeter involved. I wouldn't worry about having to do that because that was kind of specific to the example that we were working on. For problem solving on the AP test, if they give you a heat capacity and it's in just units of joules per degree C or kilojoules per degree C, that's a big C. All right. So this would be in joules or kilojoules per degree C, whereas specific heat capacity Little c is in what units? Joules per gram degree C. So you can tell the difference because here you need to multiply by grams. If you have a little c, you'll need to multiply by grams to cancel out the grams in the denominator. So that's why you need the mass. If you're given the heat capacity of an entire calorimeter, there's no grams in the denominator, you don't multiply by grams. Okay? The idea is we run the reaction in a calorimeter, we measure the temperature change, and use it to calculate Q. All right? So this is how we did calorimetry. Our process was run the reaction in a calorimeter and measure delta T. Delta T is something we can measure. Then we could use the appropriate equation to calculate the quantity of heat that was released or absorbed. And then our last step, really, when we want to measure a delta H values are usually in kilojoules per mole. They're always measured per mole of reaction. So the last step to finding delta H using a calorimeter would be to take my quantity of heat and divide by the number of moles of reaction to get delta H. So delta H would equal Q divided by N, where N equals the number of moles of reaction. Yeah. The question is, yes, H is enthalpy. One thing to point out here, I would say this is kind of a fourth step. You want to make sure the sign makes sense. So if the temperature went up, that means we had an increase in kinetic energy. So what happened to potential energy? It went down, right? You can't get something for nothing. So if you're releasing kinetic energy, that means potential went down. Delta H should be negative. And if temperature goes down, then delta H would be positive. So if temperature goes down, we're seeing a decrease in kinetic energy. We're turning kinetic into potential, so potential is going up. So really, I guess, we would say delta H, I should put a negative sign in that equation. Delta H equals negative Q over N, because it's going to go in the opposite direction. We did this in the lab. You measure the heat of solution for different things. It's not really a chemical reaction, but you dissolve various substances in water, measure the change in temperature, and we can relate that back to finding the delta H. What questions do you have about calorimetry? All right. So calorimetry is an experimental technique. That's how you experimentally measure delta H. We also talked about a theoretical way to at least estimate delta H. That is using bond energies. So the key here is we need to remember what happens in terms of energy when you break and form bonds. This is a key point that's been emphasized by the new AP curriculum. So I would expect it to come up in several different ways on the AP test. When you break a bond, you're separating two things that are attracted to each other. What are you doing in terms of potential energy? Increasing it or decreasing it? You're increasing it. So remember that breaking bonds requires an energy input. Increase in potential energy. Forming bonds releases energy. So when you form a bond, delta H is negative. So we have these numbers called bond energies. Remember, our bond energy is the amount of energy required to break a bond. So the question is, when we say breaking bonds requires energy and forming bonds releases energy, is that energy kinetic? Usually what happens is the energy that you input will come from the kinetic energy of the particles beforehand. So usually to break a bond, what happens is those particles have a certain amount of kinetic energy. Remember, particles are constantly moving, so everything has kinetic energy. But as the two particles separate from each other, they'll slow down. So they'll lose kinetic energy. And when you form a new bond, it releases energy. Imagine bringing two things together that are really attracted to each other. What's going to happen as they approach each other? They get closer, their potential energy drops. What happens in terms of their motion? They're going to move faster and faster toward each other. If they accelerate towards each other, they come together, and now they have all this greater kinetic energy than they had before. So yeah, generally that is an exchange with the kinetic energy that they have. Now there are cases where the change in potential of one reaction can be used to change the potential energy in a separate reaction. So a lot of biological systems, you have coupled reactions where one reaction releases energy and one reaction absorbs energy, and those two reactions will happen simultaneously or very close to simultaneously, so that the energy from the potential energy lost from one reaction can turn into the potential energy gain for the other reaction. And so it's not necessarily manifest as kinetic energy in that case. But most of the time, this is going to be manifest by a change in kinetic energy, which is why we see a temperature change. Okay. So when we look up bond energy values tell us how much energy it would take to break a bond. How do we use that to figure out what delta H for a reaction should be? Or at least to estimate what delta H for a reaction should be? Does anyone remember? Figure out the bond energies in the reactants. What has to happen to the bonds in the reactants? They have to break. So you're going to add up the bond energies of the bonds broken. That's a positive number. That's how much energy you need to put in, and then how much energy to get out. Do the same thing for the bonds formed. So the sum of the bond energies of the bonds formed. You subtract that one because that's going to be a release of energy. That's a negative change in potential. So don't mess up the sign here. You want to think, I'm putting in energy to break bonds. That's a positive number, an increase in potential. I'm getting out energy when I form bonds. That's a negative change in potential. So you subtract that. So essentially what this means is you can think about bond energy as a measure of bond strength. So what this tells me, if the bonds I break are stronger, so if the broken are stronger than the formed, what does that tell me about the delta H value? If I break stronger bonds and I form weaker bonds, delta H will be positive. And if I break weak bonds and replace them with stronger bonds, delta H will be negative. So we've used this equation before. We're just kind of refreshing our memories. Any idea why I put the approximately equal to? So the response was not taking into account the energy lost to the environment. Not quite. So the energy lost to the environment, we're going to take that into account, or the energy lost to disorder, we're going to take into account when we talk about entropy. But in terms of enthalpy, there's a reason this isn't exactly equal. Yeah. It doesn't always require the exact same amount of energy to break a given bond type. So if I look up a bond energy value for a CH bond, it'll give me the average energy to break a CH bond. Now in a particular compound, it might take more or less energy than that average energy. You know, there are certain things about the compound that might weaken that bond or might strengthen that bond. So when we look up bond energy values, they're not exact. They're not necessarily exact for the compound we're looking at. They're average values. So that's why it's approximately equal to. The other thing about this equation is it ignores all the other forces that may be at play. So it ignores any intermolecular attractions because it just focuses on bonds. So this equation really only works well when I have all my reactants as gases and all my products as gases. Why do I say gases? They're too far apart to really experience intermolecular forces. Yeah. So this really works well for gases, but when you have changes in phase, where there's going to be a change in intermolecular attractions, this equation doesn't account for it. So it doesn't work. It doesn't work nearly as well then, because we need to account for that. All right. What questions do you have about bond energy values? Or using them to estimate delta H? Then let me introduce the third method. Third method is using what we call standard enthalpy of formation. So standard enthalpy of formation is essentially this value we create for every substance, and we create it to give us a scale to measure enthalpy on. Okay? Enthalpy, potential energy in general, there's no absolute scale. I've made this analogy before, but if I place this calculator on the floor, and I ask you, how much gravitational potential energy does it have? People are saying, it depends. Why does it depend? I need a reference point, right? If my reference point is the floor, then the calculator has 0 gravitational potential energy. But if my reference point is the ground outside, it has quite a bit of gravitational potential energy because it's up on the 4th floor. If I brought it outside and put it on the ground, you could say, well, it's 0 then. But maybe it's at the top of a hill, and so it has more than 0. Maybe it's at the bottom of a hill, and you could say it has less than 0 potential energy there. So we always need a reference point when we're talking about potential energy. And we needed to create one for enthalpy. So what we chose was to create this thing that we call standard enthalpy of formation, also known as heat of formation. We symbolize this way. Delta H. I'll explain what that superscript means in a minute, and then F as the subscript afterwards. So if you ever see delta H with an F subscript, that means of formation. Okay? And this is something that we create to establish a 0 point on the enthalpy scale. So what is the 0 point we set? The elements. We say delta H of formation is 0 for any element in its standard state. So you might ask, all right, what do I mean by standard state? What do you think it means when I say an element in its standard state? We need to establish some set of conditions that we're going to call standard. I'm going to go to the next slide for a second and then come back. We have a set of conditions that we call standard conditions. Standard conditions mean a temperature of 25 degrees Celsius, a pressure of 1 atmosphere, and I'll come back and talk about concentration in a minute, but a concentration of each thing that's 1 molar. So the standard state of an element is going to be, well, how does it naturally exist at 25 degrees Celsius and 1 atmosphere pressure? All right, so who can give me an example of an element in its standard state? Maria? Oxygen gas. How would I rate that chemically? O2 gas, yep. Another element in its standard state. H2O, not an element, because it's got two elements in it. Yep. Sorry? All right, so carbon. What's the standard state of carbon? How does carbon exist naturally? Solid, yeah. It's actually graphite. There are two solid forms of carbon, or actually there's more than two. There's many solid forms of carbon. A graphite is the standard one. Graphite is slightly lower potential energy than diamond. So carbon, solid. Mercury is a liquid. So those are examples of elements in their standard states. They have zero enthalpy of formation. We set them at the 0 point, kind of like Celsius decided the 0 point of the temperature scale should be the freezing point of water. It's kind of an arbitrary decision, but it's one that then gives us a reference to compare everything else to. The difference is the temperature scale does actually have an absolute zero. Enthalpy scale doesn't. All right, so then for anything that's not an element in a standard state, the heat of formation is going to be, well, what's the enthalpy difference between that thing and elements in their standard states? So another way to say that is, for any other substance, the heat of formation is going to be the enthalpy change when you make 1 mole of that thing from the elements that make it up. The question is, does that mean that when you conglomerate all the elements in that substance? Yes. So the enthalpy change when you form 1 mole of that substance from the elements that make it up. So some of these can be measured pretty directly. Right? If you want to measure the enthalpy of formation of CO2, what you need to do is take some carbon, react it with oxygen to make CO2, and measure how much heat is given off. All right? So for example, for CO2, heat of formation would be the enthalpy change for this reaction. Carbon, solid, right? Standard state of carbon plus O2 gas makes CO2 gas. I should say for CO2 gas, the heat of formation will be that. Question? All right. So the question is, how would that work for really complicated hydrocarbons? Yeah, you can write theoretically what the equation would be. But the more complicated the molecule, the less possible it is to actually carry out the reaction that makes it from the elements in their standard states. This is where we rely on that fact that it doesn't matter if it takes you 20 steps to make the thing. If you take the enthalpy change for each individual step and then add them together, you can get the heat of formation of that other product. So someone has actually done all that work. Measured directly the enthalpy changes to get heats of formation for certain compounds, and then do the combinations to find the heats of formation of different things. a lot of times you get heat of formation by burning something and then referencing it to the heats of formation of CO2 and H2O and whatnot. The good news for us is we don't actually have to do any of this. These heats of formation have been measured and put into tables. So in the back of your textbook, there's like a 5-6 page appendix that just has heat of formation values along with standard entropy and Gibbs free energy values, which we'll talk about later. But this information is out there, right? You want to know the heat of formation of anything, I'll bet you could just type into Google heat of formation of blank, and for a lot of things it'll just pop up. So this has been measured for everything. We can use it then to find delta H for a reaction. So I'm going to skip ahead a little bit and then come back. These values, these have been measured and tabulated for many, many substances. So for us to find a delta H value for a reaction, all we have to do is look up the heat of formation values. And then when you want to find the change in anything, what's the general formula? Like if I want to find the change in temperature over the course of a reaction, what do I do? Final minus initial, right? So change in enthalpy is going to be just the same. Delta H is going to be final enthalpy minus initial enthalpy. The final enthalpy is just going to be the sum of the heats of formation of all the products. And the initial enthalpy is the sum of the heats of formation of all the reactants. Maria? All right, so the question is, last unit in kinetics we talked about mechanisms, and we said in some cases we're not even sure of the mechanism. This is where that principle that the pathway doesn't matter becomes important. So it really doesn't matter what the mechanism is if we know the heat, the enthalpy of the reactants and the enthalpy of the products. It doesn't matter what pathway it goes through to get there. We can find the total change in enthalpy because we know our starting point and our ending point. And then kinetics is all about that pathway in the middle, the hills and valleys along the way. So in our energy diagrams, we have hills and valleys, and delta H is really measuring our starting and ending points. So delta H is really about the difference between those 2 points. What's in the middle doesn't matter. Well, so the question is, can we use this to help us find the mechanism? Generally, the mechanism, you really need to do studies of the kinetics to get insight about the mechanism. The delta H value, the overall delta H value for reaction, doesn't necessarily lend insight into how the reaction happens. You might have some insight by looking at the bond energy values. So one thing a chemist will do when they're trying to come up with a mechanism is look for, all right, well, what are my weak bonds? What's the most likely thing to break first? And so you can use bond energy values to give you some insight and some guesses as to what pathways might be the most feasible. But this difference in energy from the reactants to the products doesn't necessarily give you much to go on in terms of the pathway. All right, so for any reaction, we can say delta H is going to be the sum of the heat of formation values for the products, right? Final enthalpy minus the sum of the heat of formation values for the reactants. So I'd say take out your formula sheets if you got them right now. So if you look on your formula sheet in the section titled Thermochemistry/Electrochemistry, you'll see this equation. It's just written in mathematical terms. So on your formula sheet, the way this looks is delta H naught equals, and then the sum of is sigma delta H0 F products minus sum of delta H0 F reactants. So this isn't an equation you need to memorize. It's there on the sheet. The one thing you need to do is just be able to interpret it. Sigma just stands for sum. Yeah. If you've talked about series in math, you would have used that sigma notation. But if you haven't talked about series, that's why I'm explicitly mentioning it now. This is the mathematical language translation of what we wrote above. Doug? So the question is, why does the heat of formation of the reactants matter? So the idea here is this. Heat of formation really gives us a scale to measure enthalpy on. When you have a given reaction, one way to think about that reaction occurring mentally, this isn't the way the reaction actually occurs, but because pathway doesn't matter, we can imagine it this way. So one way to imagine the reaction, I'm going to give myself a little more space to write here. All right, so let's say we have a reaction A plus B makes C plus D. I know, that doesn't mean anything, but we've used that as kind of our generic reaction. So let's say that's my reaction. Actually, no. Scratch that. I don't want generic A's and B's. So I want to use a specific reaction. So let's do this. CH4 plus O2 makes CO2 plus H2O. All right. We can imagine this reaction this way. We can imagine the first step would be to take the CH4 and turn it back into carbon and hydrogen. Even if that's not physically feasible, we can imagine it happens that way, right? And then we could we could combine the carbon and the oxygen into to make CO2. And then we could combine the H2 and the O2 to make H2O. Okay? So we can imagine that the reaction happens this way, even if that's not actually the way it happens. In the heat of formation values, we now have values to go with each of these steps. This first step, the delta H, would be the opposite of the heat of formation of CH4. Does that make sense? So the heat of formation for CH4 would be the enthalpy change for taking carbon and H2 and combining them to make CH4. Right? So this is going to be negative delta H of formation of CH4. The second step is going to be heat of formation of CO2. And the third step is going to be 2 times the heat of formation of H2O. So whenever we use this equation here that says sum of the heats of formation of the products minus sum of the heats of formation of the reactants, you can imagine that this is what we're doing. Notice I took the heats of formation of my products, right? In the end, when I add these together, my overall delta H would be heat of formation of CO2 plus heat of formation plus 2 times the heat of formation of H2O minus the heat of formation of CH4 . So in the end, I get CO2 plus 2 H2Os, heats of formation of my products, and then I subtract the heats of formation of my reactants, which were CH4. Why don't I include the heat of formation of O2? It's 0 because it's an element in its standard state. So that's the way the equation works, is we're imagining that we break up the reactants into their elements, and then we take the elements and recombine them. Same way the bond energy equation works. We're not actually breaking all the bonds and forming the new ones like as separate steps. But mentally, when we use that equation, that's what we're doing. We're saying, imagine we break up the bonds in the reactants, and then we form the bonds in the products. What's the net energy change? It's a similar idea. The other way to look at it is that enthalpy is really measured on this scale. We call it the heat of formation scale. And at 0 on that scale, we have the elements in their standard states. I did make the positive arrow. The question was, did I make the positive arrow smaller purposely? Most compounds that you're likely to run into, most compounds you're familiar with, would lie on which side? Probably the negative side. Why? If enthalpy is our measure of potential energy, most reactions are going to favor a decrease in potential energy. So the most stable compounds are going to be found below 0. When you look up heat of formation values for compounds that you encounter a lot in your everyday lives, things like CO2 or H2O or NaCl, down here, these are going to be stable compounds. Or at least more stable than the elements that make them up. So things like H2O, CO2, NaCl, etc. Things that you know of that are really stable, they're found down there. What kinds of things would have positive potential energy or positive enthalpy on this scale? Because remember, things with a negative enthalpy of formation, they still have potential energy. It's just relative to the elements. They have less than the elements. But what kinds of things do you think you'd find on the positive side? All right, individual ions maybe. Gaseous ions, definitely. Why would gaseous ions be up here? Because they have high potential energy, right? They're separated. They want to be together. In practical terms, what kinds of compounds do you want to have lots of potential energy? Fuels, yeah. Things up here, these are high potential energy things. You want fuels to have relatively high potential energy. The higher the potential energy they start with, the more energy you can get out of them. Yeah. So the other way to think about this equation, rather than thinking about it the way I described, as if you're actually like breaking the thing up into elements and then recombining them, the other way to think about it is enthalpy of formation is really just placing my reactants and my products on this scale and giving me a number to call their enthalpy. And then when I want to find change in enthalpy, I'm just saying, all right, what's the enthalpy I started with? What's the enthalpy I ended up with? And do final enthalpy minus initial enthalpy. So that's another way to think about it is this equation is just saying, what's the total enthalpy that I ended up with? What's the total enthalpy I started with? And doing that subtraction. But either way you think about it, the equation works. And one thing I do want to point out, I've been using this superscript. I've been using this superscript here and here and here lots. So that superscript there explicitly is pointing out that we're at standard conditions. So standard conditions are denoted by the superscript that, as in right there. So all of those superscripts, they mean at standard conditions. It's going to become more important to us further down the road, probably in the second, third lectures, to keep track of when we're talking about standard conditions and not. Yeah. So that's what that, I just wanted to point out, that's what that means. And one last little bit about standard conditions. So we say temperature is 25, unless noted otherwise. Pressure would be 1 atmosphere. Concentration, this is actually the most important part of standard conditions for us, or it will be. Concentration of everything is 1 molar. And there's a reason for that. When we talk about equilibrium, we said we measure Q, this reaction quotient. Q is the ratio of products to reactants. What, if everything is 1 molar concentration, what's the value of Q? 1. So standard conditions we use as a reference point because when concentrations change, these values like delta H or delta S we'll see in delta G, when concentrations change, those values will change. And so we set up standard conditions for what if I have equal amounts of reactants and products, what would the delta H be? And then we'll see that actually changes when if you have unequal amounts of products and reactants. So that's an important part of the standard in standard conditions. All right, what questions do you have about enthalpy? Oh, so the question about capital letter Q stands for reaction quotient. That Q is reaction quotient. From the equilibrium unit. And then the question is it as important to distinguish between big Q and small q as it is for Ks? I would say so. The one thing is some sources will use big Q also to represent heat. So context is important when you're talking about Q. Every source will always use lowercase k for a rate constant and capital K for an equilibrium constant. But some sources for a quantity of heat will sometimes use capital Q. So it can be more confusing. So I think context is important. And you want to indicate what it is you're talking about. I believe on your formula sheet when they talk about, they use lowercase q for heat. Notice lowercase q also at a different point means charge. So context can tell you a lot. But big K and little k are always distinct. Yeah, that's a good point. All right. Other questions? All right, I'm going to do the little teaser for tomorrow. The little teaser, when you listen to the radio, they're like, coming up after the break, we're going to talk about such and such, or, just watching TV. They're like, coming up next. So, coming up tomorrow. Tomorrow, we're going to talk about how randomness is one of the most important things governing everything that happens in the universe. So, entropy. This idea of randomness, it's really this complex thing that I'm not sure I really understand exactly what it means. But we think of entropy as being a measure of disorder. According to the AP, they use the definition, it's a measure of the dispersal of matter and energy. So how dispersed things are. And the second law tells us that in the grand scheme of the universe, things are constantly becoming more and more random. Matter becomes more and more dispersed. So tomorrow we're going to talk about how this randomness really comes into play. And we'll formally look at, well, how do I tell? How random are things? How much entropy do things have? And how do I compare them? To be continued.